So we have already been talking about input features, the linguistic features. So we are going to talk now about the output features, which are at the output of the DNN, and these are the acoustics. Okay, acoustic features. So these ones have some requirements, basic requirements. That first of all, they should be extracted from the waveform. So we shouldn't use any other source of the information. Also, they should be suitable for modeling, and we need to reconstruct the waveform from these features. So they should completely describe the signal, or in some smart way that we can reconstruct later the signal. Okay, that's the main that's a big difference with the features extracted for ASR, for example, for this reason. So we're going to talk about acoustic feature extraction and engineering. So this is two parts in acoustics to develop the output features in the DNN. Okay, so let's talk about this example. So we have here two waveforms, two segments of waveforms, and they represent the same phoneme. Okay. However, if you take the waveforms and you want to put these waveforms at the output of the DNN, it's not very easy for the DNN to predict or work with them because they are very different, even though we know that they represent the same phoneme. Okay, so you see, if we want to, for example, compute the average of these two shapes, waveforms, or compute some, we need to compare these waveforms, we see that they're very different, even though they meaning the same thing. So they mean the same thing. So how about if we extract the spectrum? Maybe in the spectrum domain we have some more meaningful behavior of these two waveforms. So if we take the spectrum, if we compute the spectrum using just the regular FFT, we will see that these waveforms, you can recognize some pattern that it is similar, but these curves are very different. And you will see that if you subtract one of the other, you will see that there are a big difference. Okay, so so at the end there is one solution. One of the possible solution is to just extract the spectral envelope, which is the counter of this spectral magnitude. And if you compare these two curves, now they are much similar, and they look more similar, so more consistent with this meaning of the underlying waveforms. They mean the same phoneme, right? So that's the reason why we need features and why we don't use waveforms directly. There are some attempts of using the waveforms directly. They work, but not. There are some disadvantages. Okay. So let's talk about some terminology about the features that we are going to extract. So there are essentially three features. The first of all was already mentioned, is a spectral envelope, which is the counter of the magnitude spectrum of the signal, and that resembles, or yes, the shape of this curve resembles the frequency response of the vocal tract. Okay, so you can see that the formats or the values of this frequency response. Also, we want to extract from the waveform this second feature called the fundamental frequency, or F0, which is the frequency in which our vocal folds vibrate. Okay, and the third acoustic feature we want to extract is just a periodic energy, or the periodic, the periodicity, which is nothing but the degree of randomness or degree of aperiodic energy in a certain band of the spectrum. So in this example, in the right-hand side, in the high frequencies, you see there is more randomness, there is more aperiodic energy, and in the low frequencies, you see less aperiodic energy compared to the harmonics, compared to the periodic energy. Okay, so we have these three acoustic features we want to extract from waveforms, and for that task, we are going to explain one of the vocoders or systems to do this task, which is the world vocoder. And we use the world vocoder because it is open source, it's free. It is very well programmed. It's very standard. The way how it works, it's stable, and we have some receipts in the Merlin toolkit to work with the world directly. So it extracts, as I mentioned, spectral envelope, fundamental frequency, and band periodicities. So let's talk about how it extracts the first feature, which is the spectral envelope. So first of all, it takes the waveform. So let's think about the waveform inside uterines, complete uterines, and this just split in chunks with the length of 3 pitch periods. Okay, each one of these chunks, and then these chunks that we call frames are multiplied by a Hanning window, as you see in the example. That's the first step. Then we compute the magnitude spectrum using just the FFT, normal operation. And the next step, we just smooth this magnitude spectrum to get rid of the spikes that go to negative numbers. So the spectrum looks more constant, more stable. And then we add another smoothing process in top of that. And now we see that the curve, the green curve, starts looking more like a spectral envelope. It's not ready yet, but it looks more like a spectral envelope. And then last step to extract it is just we take the green line, which is the smoothed version of the spectrum, and we do some. There's the world of vocoder do some weighted sum of shifted versions of the green curve of the smoothed spectrum. Okay, so we have the smoothed spectrum multiplied by Q0, which is just a coefficient. It's a number that the people that developed the world found just empirically, and that is summed by just shifted versions of that. And as a result, we'll have the spectral envelope that is in this example is the line in color red color. Okay, all of these steps are actually made in a encapsulated domain, but for this in order to illustrate what it is doing, we are explaining in frequency domain because it's more illustrative and it's more easy to understand. Okay. Okay, so this is the first feature, acoustic feature, spectral envelope, and for the second feature, the fundamental frequency, we are not going too deep in the process of extracting this feature, but I would like to mention how the output looks, how this fundamental frequency curve looks, and it is assigned a 0 Hertz frequency for frames that are unvoiced, and for frames that are voiced, just the frequency, the extracted frequency in Hertz is assigned. Okay, in this case, these values are between 100 and 140 Hertz. The third acoustic feature is the band periodicities. That is a degree of randomness or a periodicity in a certain band. So in this example, we have 3 bands, and if you focus on the band A, you see that the spike in the middle. If you take the energy of the spike in the middle and then you compare to the energy, total energy inside that band, you'll see that it's very high. It's a very high number. Okay, and in the band C, you'll see that it is completely the opposite. Okay, so the band periodicity is defined as the total power inside that band divided by the energy of that spike, which you can define as a sinusoid. Okay, so in other words, if there are some harmonics in that band, the band periodicity will be low, and if there are no harmonics and they are more random or more aperiodic energy, that value will be higher. Okay, so so far we have extracted the 3 acoustic features, but actually we have just extracted the raw vocoder features. Okay, so there is an extra step that we need to apply to make this DNN to work correctly with these acoustic features. Okay, so far these raw vocoder features are very high dimensional. For example, the spectral envelope, the size of the spectral envelope is the half of the FFT length, which could be 1,000, 2,000 or more coefficients. So we need to compress that information, and we need to adapt that information to work in a proper way with the DNN. So this process is called feature engineering. So you see there that we need to compress the length of the vectors. And this diagram summarizes the whole the acoustic feature engineering. Okay, so at the input, at the top of this slide, you have the raw features extracted by world, by the vocoder, and then we want to modify these features to make it work with the DNN, to adapt this feature to work properly with the DNN. So, I want to mention that all of these processes here are inherited from the old HMM-based speech synthesis. So there are many things that we should modify in the future. You can think about how to modify or wonder or research about this. So we can start explaining about the first process. So we take the spectral envelope, which is a very high dimensional vector, and then we transform to Mel-Kepstra, which is another domain. And if you take just the 60, in this case, in this example, the first 60 coefficients, you can retain most of the information of the spectral envelope just in the 60 coefficients. So you compress a lot the information. You compress from 1,000 or 2,000 coefficients to just 60. In the case of the fundamental frequency, we do two things sequentially. First of all, we just apply a logarithm of f0, and then we interpolate the f0, right? So I'm going to show you why we do that. And that is because the DNN, the output of the DNN is the Gaussian, so it's unimodal. But if you see this curve, it has a lot of numbers or data around or from 90 and 140 hertz, but also it has a lot of data in 0. Okay, so that means that the distribution of this data is not unimodal, it's not Gaussian. We need to enforce this to be Gaussian. So for that reason, firstly we apply the logarithm to f0, and then we interpolate the unvoiced frames. So we remove the 0 hertz. We just interpolate from the last voiced frame to the next first voiced frame, and in that way we have all the values around 100, 200 or something like that. But we get rid of the zeros. Okay? With that operation, we enforce the Gaussianity of this feature, but we remove the information which frames are voiced or which frames are unvoiced. So we need to append another feature, which is the voicing decision, just a binary saying that this frame is voiced or this frame is unvoiced. Then the next, the next step is the normalization, and there we just normalize the features by the mean and variance, just to make them have the same range, more or less, so they can have a same weight, more or less a same weight inside the DNN. And at the end, we just append some deltas and delta-deltas, which are the dynamic features. They try to have the degree of how these features evolve over time. All of this is inherited from the HMM, so there are things that we can re-engineer. So if you run that script 3. Prepare acoustic features in the Merlin toolkit. The main lines are to run the Python script, extract features for Merlin. You need to provide the Merlin directory, the input WAV directory, the output directory where the features will be stored, and the sampling frequency. So let's take a fast look at this script. And the first thing is that Merlin so far just works with a 16 kilohertz and 48 kilohertz sample rate. So there are some fixed variables, fixed values for alpha and FFT length for these different sample rates. So you need to be careful about that. And you'll see in this script that runs world to extract the features and then uses SPTK to do most of the feature engineering. Okay, so this is a video as a demo showing how to call this script, and you see that it shows the usage if you don't provide any input argument. Then you can check your data, the sample frequency of your data that should match with the sample frequency that you provide in the global config file. So in this case, 16 kilohertz. Then you can call run the prepare acoustic features, giving the input directory and the output directory. And world and SPTK will extract the features, will do the feature engineering process. Very quick in this case because we are running in parallel in multiprocessors. And at the end, you can just check, for sanity check, that the label, the features are stored. So you say that it created the BIP, LF0, and MGC directories. Okay, so at the end, we can wonder, or we can research about these things that there are many decisions, or there are many options that we can try. So for example, we can use fixed frame rate, or we can use pitch synchronous frame rate. Internally, we saw that the world uses, it extracts the pitch and it works pitch synchronously. So maybe we don't need to work in fixed frame rate. And we use Kepstrom to compress the data, to compress the spectral envelope, but maybe we can just do the same. We can compress the spectral envelope in the frequency domain, and the use of Kepstrom is just because it has an advantage in HMM speech synthesis, but it was inherited. So maybe now that we are using DNN, we don't need Kepstrom anymore. We can use, for that reason, we can warp the frequency scale, and we can compress the coefficients, the frequency coefficients. We can play with the order of these coefficients. We can use 60, 45, or 80. We can interpolate F0 or use another solution to keep the Gaussianity. And also a very important thing that has not been mentioned is that so far we have not modeled, or we have not structured anything related with the phase of the signal. So we are presenting in this interspeech on one workoder that extracts magnitude spectrum and also phase spectrum, and you see the difference. It makes a big difference. Okay, and also tachotron is another way to recover the phase, but the phase is not modeled, it's not extracted, it's just recovered from the magnitude spectrum. So yeah. So far we have been talking about defining the problems of TTS. We talk about the linguistic features and the input and the acoustic features of the output of the DNN.